Okay, so today we're doing the review for the exam, and I've written part of the exam, but it's the format is going to be quite a bit more like it was for the second exam last year, because then actually that was when full COVID was on. So it's going to be it's a little bit more. I'm kind of require a little more thoughtful answers. Since I can't rely on the closed book, so I can't. I have to kind of at least have some tougher problems. But anyway, so let's just get going. Let's get into it. Yeah, it's going to just basically be so similar to this. I mean, this is your VT 2022. There will be some kind of description. Basically, on these one here, I mean, it does actually count. Like when you basically give these short answers, don't just give like one sentence answers. I mean, generally it's like a paragraph, right? And something that, to try to kind of write it well. Don't just scratch stuff down. I mean, I can't. It's not gonna go well. There'll definitely be a problem kind of like this where you're set up. I kind of describe a schema or a database domain, and then okay, good. So people can hear. And then maybe shows a little bit of data, and then so you have to kind of understand this here, the description. So I try to keep everything kind of minimal and very terse, but you have to kind of at least understand some of the language, and then basically answer queries. So this is in the relational algebra. So it's very important that you understand what the basic relational algebra is, the extended relational algebra, tuple calculus, and SQL. It's very important that you. I mean, I hope I don't have to remind people what is the difference between like standard relational algebra and the extended relational algebra. And so when I say standard relational algebra, then also the assumption is it's going to be under set semantics, whereas the extended is going to be under bag semantics. And then tuple calculus is always under set semantics, and SQL is always under bag semantics. Okay, so understand what I just said there. There will be an uploading, like there will be like where you're gonna have to scratch out an ER diagram or something, basically with that only PDF. If it's any other kind of exotic format, I'll just ignore it. Okay, so it's got to be in PDF. You've got to convert it to PDF. Yeah, and then these are, the normalization theory ones are going to be kind of the same old, where I just present a universal relation, a set of functional dependencies, and then I just basically say put it into 4NF or BCNF or 3NF, and then I might have some kind of smaller examples where I just say, well, what are the candidate keys? What are the prime attributes? What are various things like that. Yeah, the XML stuff. Yeah, sometimes it'll just be kind of like, can you scratch out do you understand at least the concept well enough to kind of scratch something out? Anyways, that's good. Again, when I write exams, I try to make it so that there's a couple tough problems, but most of them are going to be fairly straightforward if you've done the readings and you understand the basic concepts. Okay, so that's kind of the philosophy. So I guess with that, are there any direct questions? Somebody asked here, was prime attributes the ones that exist in a candidate key? That's correct. Can we upload PDFs for the other questions too, or only the ER diagram? It's only going to be the ones that I ask for. So it's probably going to only be the ER diagram question that you're going to upload PDFs. Otherwise, we want to keep it kind of straight Cambro. That's that. So I guess the thing is that people have mostly had questions about like specific problems. So I guess if I just go back to my email here, I'll give some priority to the people who kind of put in their, okay, the first, okay, so one of the first questions was considering the functional dependencies. Let's see what problem is this. All right, well, maybe got some other questions. I'd rather kind of deal with things kind of interactive here. So anything in the chat, anything you put in the chat will always kind of get my attention. So Tony up. Okay. What about normalization decomposition? Can we send a no? Sorry. I mean, there might be a question where I would expect that, but it's going to mostly be. Well, okay. So let's see here. I mean, how many people want to do? How many people would prefer, instead of like writing stuff out on? I mean, how many people really do want to upload a lot more PDFs? I mean, I'm not going to have PDFs for everything. The problems that you can. I mean, okay, how many people would be? Maybe the normalization algorithm problem. I should actually ask you guys to do it in PDF. But if that's the case, then it's going to only be PDF. So in other words, okay, so let's just okay. How many people? Just hands up. I want to just do a kind of a quick poll here. Raise your hand. How many people have a problem with doing the normalization problem, like the decomposition algorithm, the top-down algorithm, whatever? How many people have a problem submitting that as a PDF? Does anybody have a problem doing that as and submitting as a PDF? I don't see anybody raising their hands. Okay, so the normalization will also be done. I'll let you guys do that in PDF. Maybe I'll do a lot. I mean, how many people prefer doing stuff on PDF? So you have to kind of have your own tool that you're using and then convert it into PDF. How many people prefer that as a general? I mean, now when it comes to like define something, like give me a definition of something, then it's going to be typed in. Okay, but with it, maybe I'll try to more tilt things toward. Yeah, so we're like for relational algebra and stuff like that. Okay, yeah. I'll make a note of that. So it'll be more PDF, but just be careful with this, because if you don't, if you screw up anyways, it's got to be there as PDF. Okay. Let's see here. Right. So, so there was somebody who was saying, I'm wondering about the exam. Let's see here. A goes to UST. All right, I assume everybody's got the exams in front of them. Okay, that was 20. Okay, 2020. Here, let's do this one. Yeah, this one. Okay, so does everybody have the problem? Basically this problem here. Can everybody? It's basically it was okay. I'm going to do this problem now. This is the problem I'm going to do. I think that what people had a problem with was that there was a. All right, here, let's see. I'll just. Is it okay if I do that problem? Okay, I got some direct question here, which looks pretty good. This is exam V. This is like the second exam in 2020. Everybody go to the normalization problem. The second exam for 2020. Okay, good. I got an interesting, a good question there. So, all right. So let's do that. Good. Somebody. I'm not actually sure if that is the right one though. Let's see here. Yeah, that's right. Those are the list of the exams. Okay. So go to the one. All right. So what do we have for the problem here? Actually, I'm going to do it. I'm going to use a pen. Okay. So we have the relation R U P N C S T H I. All right. So these are little funny names here. I don't know what I was doing here, but I'm sure that I had an idea of a real world case in mind where these stand for something. Okay, so that's when you see me doing this, it's just for my own intuition, so that like, I don't know, C could stand for course or something, S could stand for section. I don't, God only knows what it was. All right, so here are the functional dependencies. A goes to UST. CST goes to H. UPN goes to I. And A goes to P and C. All right. And for this question here, let's see, what was the specific question that somebody had sent me earlier? They had an issue about this problem. How does one handle such a question when there is an attribute A that does not live in R? Okay. Oh. That looks like a typo. Well, that was kind of dumb of me. I mean, the way you do that is you probably somebody did send me a message during the exam and said, I mean, there weren't that many people who were taking the second exam, as it turned out. So I didn't have that many that helped debug it. Listen, the point is that if you see something like this, then Minak is being a dunce. I'm being stupid, because this makes no sense. I mean, I would say, consider the following functional dependencies for R. Well, let's just take it at face value. Listen, I mean, if this is R here, if you have to answer this thing, it was stupid. This is kind of a dumb question, because I would never do that and say when I'm saying doing a BC and F decomposition, I'm saying doing it for the full universal relation, because otherwise it's kind of like, what's the point? But let's just if these are the functional, if we're strictly speaking, if these are the functional dependencies, then this one doesn't, this right here doesn't apply, and nor would this. So really you're just settled, you're just left with this. Sorry about that. So basically, yeah, so because these have a happy home here, these have a happy home there, I hope. So then if we were going to do that, then basically what we would say then is we would say that, well, is CST goes to H. This is not a super key of the of that relation there, right? So we would basically then decompose this right here would decompose into R prime, I should say R1 CSTH and R prime. And then what would R prime be? R prime would just be basically all this minus H. So it would be UPNCST, no H, but I. Is this one here then? Is this one here in, now that we've done this decomposition here, is this in BC and F? This is the only one that has a happy home there. Nothing here has a happy home there. And this winds up being, this is a super key of that. So this is fine. And then if we go over here, we would say, is UPN goes to I. Is UPN a super key of this? No. So then what we do is we say R2 UPN I, and then the rest of this winds up being R, and then we'll just call this 3 because we know we're going to be done here. UPN CST. Okay. So, anyways, that was that. So, yeah. So I'll. This is why it's important to kind of, if you see some bug in the. I mean, I think just because there was like maybe 3 or 4 people that signed up for this exam, I didn't. Yeah. I don't remember what happened with this, but I think somebody sent me a message and I just basically told people they could ignore these 2 functional dependencies. But anyways, that's how you do it. So is there Yeah. Okay. So that's that. Let's see here. Okay. So now let's. Okay. So there was sticking with normalization theory here. It looks like I got a question here in the. In the following question in this exam, the 4NF question, I assume that R is supposed to contain U. That's right. I don't understand how this happened. Yeah, so if we do that. Okay, so if we're going to take this to 4NF, let's do it. Remember, when you do a 4NF decomposition, the point is that basically you're testing to make sure that, I mean, this is is this, okay, here's one question for you. Is this a non-trivial multi-value dependency? And the answer is yeah. They're trivial when basically the whole thing, like if you had this R, X, Y, and then you have X multi-determines Y, that's trivial. That's always the case. Okay. I mean, that's not saying anything. All right. So so in other words, it's got to be a non-trivial multi-value dependency. So this is non-trivial. This is non-trivial. So you always want to do those ones first. And is this right here is a super key of this relation here? Absolutely not, because with A you can get to U, and with A you can get to C, but you can't get N and T from A, right? So therefore, what do we say then? Then we basically say that we're going to decompose it. So this is going to decompose into RAT. And remember, this A here is not a key of this. So you don't underline, you don't make it a key. And then, but you do the same kind of decomposition here. So the T is then going to drop out, and we're going to have R prime A, C, N, U, right? And then we can come to the next one. Is this over here, is this a non-trivial functional dependency? Is A super key of this? First of all, it's not trivial. These aren't, this is not all the attributes, so it's not, you don't have to worry about that kind of level of triviality. And then is A super key? No, absolutely isn't. So then to get to 4NF, we have to kind of use this to decompose, and then we get R2 A N, and then what comes back over here then is going to wind up being R3, or I'll say R double prime A C U. Okay, and then these are the only ones that apply. The functional dependencies that apply. Is A super key to this? Yes, yes. So this basically this is done. So this is the decomposition into 4NF. All right, let's see if I got another question there. Okay, so just, will A be underlined in R3? Oh, I'm sorry. Yeah, good point. Yes, that becomes the primary key. All right, so let's see here. I got some email here, more email. I got so much. Kind of have to kind of sort through here. All right, so there was a question here about what is, I mean, the top-down algorithm that we use in this course, or the one that I developed, is actually a little bit simpler than the one in the book. The one in the book maybe gives you a little bit better decompositions, but mine is always guaranteed. It's absolutely the simplest possible way to kind of grind out the algorithm. I mean, there's a certain disadvantage because it's like this. Let's just do a really simple example of a top down. A, B, C, D. A goes to B. A goes to C. And B, C goes to D. I think we have some. Is there a question somebody has, or is it just one second? I gotta use my executive powers here to mute. Oh no, there is a question. Or anyways, there is somebody who has their hand raised. Is that something I should address? The person with the hand raised, just speak up if you want. But okay, I guess it was probably just left over from the survey. Okay. All right. So this is the top down. So how do we do this in top down? Now, I think that what the book talks about is it talks a little bit about, okay, it would be kind of stupid of us to do it. I mean, but let's see here. I got a little bit of problem. If I say, things, I mean, if we want to get a nice decomposition, see, the point is if we run the top down using this right here, what we're going to wind up getting is we're going to wind up getting kind of something a little goofy, because we're going to first say, well, AB, that's going to be its own relation, and AC is going to be its own relation. But the truth is that if you're really going to do this in practice, you would want to combine these two. So the question is this: if I say AB goes to AC, is this equivalent? Is this equivalent to A goes to BC and BC goes to D? Are these equivalent? And equivalent in the following sense, that is, that is the closure over these equal to the closure over these? Anybody have? Yeah, exactly. It is. So with A, because with AB goes to C, you can definitely get A goes to B and A goes to C. And with A goes to B and A goes to C, you can definitely get A goes to BC. So they're going to be equivalent. This one here would be better to do a top down with. But when I say do a top down, I'm just saying grind it out with a set of functional dependencies. I'm not talking about getting a good one, good in the sense that it minimizes the number of tables, right? It does the same thing, but it minimizes the number of tables. I mean, it certainly is you're going to get a better result if you run with this, because you're going to get, this takes 3 tables. This will give you 3 tables, and this will give you 2 tables. And by golly, generally speaking, we want to keep things simple. So we probably want to use this one. But I think the question is that, well, let's take this. Let's take this right here. Forget about this. And let's just take these 2 functional dependencies, right? And what we want to do here is we want to do the top-down algorithm. Okay, so how does the top-down algorithm work? We start out with what's called the universal relation. Has all the attributes. These are the 2 functional dependencies that we have to consider right now. And then the question, here's how the top-down algorithm works. We take our set of functional dependencies. Okay, here's our set of functional dependencies. And we walk down them from top to bottom. And we're doing it relative to this universal relation here. Now, remember, BC and F means that if it's a non-trivial functional dependency, this left-hand side has to be a superkey. Now, I asked everybody, is A a superkey of R? Yes, good. Everybody knows that. Yes. Okay, so this is fine. This checks out with a nice green. Actually, this thing right here doesn't really give me a nice green. It gives me a yellow. Do I have a green on this thing? Okay. Yes, so that checks out with blue. Now, we come to this one here. Is BC a superkey of R? Good. No. Yeah, it is not. So therefore, what we're going to do is we're going to use this guy. So it's not. So we're going to use this guy, and this is why it's called top down, to split this top down. So from the top going down. Okay. So now when we split, if we have X goes to Y, and we're using X goes to Y to split this, then basically, and it's over R X, Y, Z. So Z is the part that's not X, not Y, right? So Z. So in this case, if we're using this right here, BC right there, that's X, Y is D, and A is Z. Okay. Anyways, what we're going to do, if we do that, when we split it, we basically say X union Y and X union Z. Okay? That's what winds up surviving this. So the split goes like this. So we're going to use this to split. So basically, it means that we're going to have an R that's going to be BC and D, and then we're going to have another one, which is going to be BC, and then with the Z here, A. Okay. Does that make sense to people? So that's R1. So and this one here is R2. Is there any down top algorithm too? Well, the down top algorithm, well, it's essentially the synthesis algorithm, that 3NF algorithm. We can do this in 3NF as well. I'll do this in 3NF as well. So that's the top down and bottom up. Bottom up, you could say that's the 3NF algorithm, or it's what it does instead. It works from the functional dependencies and then builds upward from there. Right. But anyways, I hope the question I had, I hope this clarifies a little bit of what top-down algorithm does. Top-down algorithm, you can use it to calculate BCNF or 4NF. Okay, it looks like we might have some questions going to go away from normalization theory in a second here. Let me just make sure that, just to keep it kind of complete here, let's try to kind of finish let's try to finish up the normalization theory, at least to kind of get it kind of in a, okay. All right, there's that. I'm just looking at some of the other questions. Yeah. I do apologize for everybody about that. I mean, about that confusion with the missing attribute in the universal. All right, somebody had a question on 18.1. Does anybody have any really kind of basic question about normalization theory now? Maybe I'll just kind of continue with this here. So keep it really, really basic. I'm going to do the 3NF of this as well. All right, so the 3NF of this basically is going to work the following way. 3NF, what you do is you basically look at these right here, and the first thing you do is you say, the first thing we do with 3NF is we say, we're going to have to just basically say, put everything into this standard form where we have just one attribute on the right-hand side. So we can always rewrite stuff in that way. BC goes to D. All right, so that's this is the first thing we do when we, we put all of our functional dependencies into the X goes to, maybe I'll make this script A. That's a little script A, so it's not specific A, but it's just a single attribute. What this right here does, basically it says, okay, fine, we've done that. We put everything into that form. Now, are these in and of themselves, are there anything, is there any redundancy here? And there is no redundancy. So you can't use this to get that. And okay, so this is a minimal cover. All right. And then what we do is we just simply group by the left-hand sides. And then based on each group, we define a relation that covers all the left and the left and the right-hand sides of that. So this basically means we get R1, A, B, C. We have A here because that's the group, and then B is there included, and then C is included. And then we have right there, we have this guy right here. So R2, B, C, D. So in this case here, I mean, the top-down algorithm and the bottom-up algorithm, or the synthesis algorithm for 3NF, they're giving the exact same answer. Okay. All right. So is a super key. Yeah, if we go back to that 3NF, the 4NF example, the thing is that when you do 4NF and then you get to a point where it's like, oh, I've done the 4NF and I get this, I said, oh, A, B, and there was I think there was A, C for the, these were kind of coming off of the 4NF decomposition, but these are not keys. And then we have the multi-value dependency. A goes to B here. But remember, A goes to B over a relation like this is trivial. When you have X goes to multi-determines Y, and it's over R, over Rx, Y, that's always a trivial function of a multi-value dependency. So therefore, this right here, it basically says that A would have to be a superkey if this was not trivial. But since it's trivial, then it passes 4NF. It's a little bit of a kind of the way the definition works. That's why we can stop here and say that we're done with 4NF. Okay, good. Do you always group the left-hand side? Yes. On the synthesis algorithm, yeah. Yeah, you definitely want to do the grouping. I mean, I guess strictly speaking, you don't have to do the grouping, but it's kind of it's kind of an integral part of the algorithm. I mean, if you leave it out, does it still give you something in 3NF? Yeah, but is it something that's kind of not as nice? Yeah, it's not as nice because it doesn't. I mean, it kind of breaks things up unnecessarily. It's overly complicated. I mean, you get too many tables out. All right. I mean, remember, 3NF and BCNF are just definitional. Something either holds, it's this decomposition is holding 3NF. This decomposition is holding BCNF or 4NF. So it kind of goes that way. All right. Are there any other normalization questions? Because we could maybe leave normalization behind a little bit. Because I had I saw some other questions in the chat. I like to kind of more focus on what comes up in the chat because let me just review the chat here. All right. So somebody says, I have two questions. Given the relations AB and SBC, all right. Remember, RAB, natural join, right? That's not a theta join, that's a natural join. S, BC. All right, so just remember that natural joins are a little bit of extra sugar. What this will give us is that this will give us a table that has a signature. This will return res A, B, C. Ooh, that doesn't go so well. Some result table A, B, C. I mean, really, what I should be doing here is the following. I'd say basically that R equals, well, R is a table that R is defined as we have RAB and we have SBC. Okay, that's what those tables are. And then what we do is we basically say R, because this is not actually the right syntax here. I'd say res equals R natural join S. This actually will have, this will result in a table with 3 attributes, whereas R Cartesian product, R dot B equals S dot B. This will actually give us something that has 4 attributes. 4 attributes will plop out of this. So I think that might, so they don't equal each other. I see. So yeah, that thing that was maybe a true-false question. What two SQL keywords are necessary in the table X? Oh yeah. So if you want to delete, basically the answer to that, maybe it's okay. It's like if you want to delete table S cascade. So that's the second word. It basically just says that propagate the deletions onto whatever like the foreign keys are. So if something, I mean, foreign keys are pointing into A, into S. What it will do then is it will delete those, the table, it will delete the references to the table from the other. Well, what it's going to do, let's see. I mean, what it'll actually wind up doing is it'll wind up removing other tables. But this, I won't have questions like this because these are such easy questions to kind of go and look up when you have a book. Okay, let's see here. What else? Let me see what else I got here. Right, normalization. I'm just trying to get it so that I have the full chat covered. Yeah, we'll do the PDF. How to do the core relational algebra expressions related to tuple calculus? Well, they are representationally equivalent. So the with core relational algebra, you should. I mean, if you the languages are equivalent. So basically, anything you can express in tuple calculus, you can express in core relational algebra. Anything you can express in core relational algebra, you can express in tuple calculus. But then the exact way that they interact is a little bit more tricky because you can write code, but it's not completely trivial that will take a tuple calculus expression and turn it into relational algebra. You can also write code that will take a relational algebra expression and turn it into tuple calculus. Okay, so you can reduce one to the other, but we didn't cover that reduction algorithm. There's a little tricky thing. It's just basically definitional, but there's some there's a fair number of moving parts. So we didn't go through it. But if you say something like, well, what's clearly we say something like this, we say project A from R. That's equivalent to whatever that gives us is going to be equal to something like x dot A such that right. These give us the same set, right? And we get where it gets complicated is where the exist. So basically, what you have is the exist turn into joins, the not exist turn into like minuses, right? Set difference, but it's not that trivial. And then the for all winds up being wind up getting kind of macro expanded out into the definition of division. Okay, but it's a bit beyond the scope of the course to kind of intricately go through those different transforms. Okay. All right. Okay, so I'm moving on the chat here, kind of scrolling down on the chat. All right. Question 1 on exam. There was a question. Here is question number 1. Oh, the question number 1 was, what are the 5 fundamental operators in core relational algebra? How do these relate to the tuple calculus? Now I see where this is coming from. Yeah, so basically the answer there would be that, well, what are the 5 core operations, project, Cartesian product, union, minus, and then what else am I missing here? Select. So what I'll be looking for is that. And somebody might say, well, what about this instead? Instead of union, they have intersection here. Okay, that would also work. All right. All right. Did you say that A was a super? Okay. Okay, now it looks like we have a question here. Part 2, SQL queries in tuple calculus that sets are a superset of the set with, okay. So somebody asked, just the purpose of, the purpose of the lecture today is that I try to answer as many questions as possible. And if that involves me doing old exam problems, then yeah, I'll do that. I mean, that's a legitimate question, but I kind of prefer, if somebody has a direct question, I prefer just to answer that because it's more efficient, it feels. But it looks like right now we have this the sets problem on. I mean, this gets a little bit tricky actually. This SQL queries for the, let's see. Okay, in tuple calculus, the sets that are a superset of the set with ID. So we have the ID of an object. Let's see, set in. All right, I'm going to back away. I'm going to hold off on answering that supersets question because I think that it's going to take a little while to kind of set it up. I'd rather kind of get. And I think one of the problems also is that it's. We'll definitely do it, but let me just see if there's anything kind of simpler to start out with. Let me go back here. Okay, looks like people do want me to. All right, let's do this thing. Okay, so here we are. We're going to do this problem with SQL queries on the second exam last year. All right, so here's how you would approach something like this. You would first you would look at the problem. So this is I hope that people have this problem in front of them because I can't. This camera is not the greatest. But basically, it's this thing where we're looking to manage a barter system. Okay, so what you do is you look at this thing. First, you kind of say, okay, we would like to manage a barter system. So it looks like people are going to be trading things. This is exam VT202. So this is the last exam that was posted on Cambro. And it's part 2 of that, the SQL queries. So I'm just going to assume everybody has this in front of them, or they will, shortly. Okay, we would like to manage a barter system where certain sets of objects can be traded for other sets of objects. Yeah, because that's how barter would work, right? You would say, well, I'm going to trade. Yeah, I guess we're going to have some examples here. For instance, we can trade a Snickers bar and Coca-Cola for carrot, milk, and an apple, and that's yeah. So you have a Snickers bar and a cola, and you want to be more healthy, so you trade that for a carrot, milk, and an apple. All right. So what we're dealing with here is we're dealing with sets. All right, so we have to kind of represent sets somehow in SQL. So here's a schema to represent this. So the schema is basically we have object, all right, and so the object is going to have an OID, an object ID, and then it's going to have a name, like Snickers, and then it's going to have a type like candy, right? Great. Okay. And then we have a set. All right. And a set has an SID, and it's just a unary. So we have like the set number 1, the set number 2. And what we're going to have is we're going to make it. We're going to have this is the critical thing that joins these, and that is the in. So some object is in some set. Okay. So, I mean, you might have like 20 objects, and then you might have okay, if I have 10 objects here, so I have 10 different objects listed here, how many possible distinct sets are there? Strictly speaking, we want to do this, by the way. And this is always true, but it's kind of, let's just make it kind of explicit here. So in other words, we don't have repeat statements where we have set, some objects inside of a set. Anyways, the short answer here is that if we have 10 objects, then we can wind up having 1,024 different sets, right? Because all the different possible combinations could be accounted for in this right there. Okay, so great. And then we have fair trades. Fair trade is basically from set to set. So this is basically just saying that some set, you can trade this set to that for that set and get that exchange. This is kind of an example of a constraint that we can't really enforce in SQL, but we might want to say something like this. This has to be symmetric. Or could we actually express that in SQL to make it so that this has to be a symmetric relation? That would wind up being a key. I suppose you can make it so that could we express this in SQL that we want this to be symmetric? That's kind of a curious question. That's the primary key. I don't know if we can, but you'd want to just flip these and make sure that that's also included in. You want to have a foreign key pointing back to it, but that you somehow flip from to. You probably need to use a trigger to do it. But anyway, so that's a separate thing. So right, I don't make any statements about whether this is symmetric or not, but it probably should be symmetric. Okay, in possession basically just means that I'm not really sure if we're going to use in possession. Just maybe it's like whoever owns the database. Do I possess that set? Or do I possess that object? Okay. So this database is relative to a single person. So in possession would mean something like, okay, I have this object 1, 2, and 3 in my possession, which means a Snickers, a cola, and a carrot. They're in my possession. Okay. All right. Yeah. So I hope that's clear what's being set up here inside this database. Is it clear? Kind of what we're trying to represent? All right. So now let's get to the queries. So the queries are the first one is in relational algebra, give the set IDs that contain a member of the object of type pop. Pop is a Michigan way of saying lesk. Soda is more the East Coast or West Coast way of saying it. But flyover country people say pop. And that's what I grew up with. All right. Extended relational algebra. So I'm just going to say this very quickly. I think that these ones are going to be easy. In relational algebra, give the set IDs that contain as a member an object of type pop. So that would be these. You basically do a natural join here from set to in to object, and then type equals pop, and then you just project out the set IDs, right? Yeah, in possession. Sure, I'll put it there. In possession. And that's going to be an object ID. Okay, so anyways. All right, the extended relational algebra, the set of IDs. In extended relational, the set of IDs paired with the number of objects in the set the set IDs paired with the number of objects in the set. All right, that would basically, all that would be basically then is it would just be, we'll do a natural join natural join SID within to object. That would give us a table that has set ID, object ID, name and type. And then what I would do is I would basically just do a gamma operator over that, where I do the count of I project out with the gamma operator, I project out the SID, and then I also do a count of the OIDs. Actually, in this case here, I just need these two tables here. So the second one, in relational algebra, I'm sorry, pop is just, it's the type. So type was pop. It's just like type could be pop, it could be candy, it could be, so it's not a computer science notion of pop. It's what people call lesk. Okay. All right. All right. So, okay. I think that I hope that people understand. Okay, we'll do the first problem here. So here's the schema. Let me just do this. The first problem was just give us the relational algebra that gives the set IDs that contain an object of type pop. All right, that's going to be just these guys right here. So let's just that. Okay, relational algebra. It's going to be just set natural join in natural join. Okay, now I'll just do this here. Type equals pop, and that's over object. Okay, does people see that? Set natural join in natural join. I'm grabbing up the pop. All right, and then all I have to do then is we just want to have the ones that contain that. So I just then project SID. All right, so that's the answer to the first question. Yeah, you could do the selection, the sigma. You could do that. You could do that out here as well, right? So but I just did it here. All right. Yeah, I guess I just kind of assumed we were just going to muscle through. Yeah, maybe why don't we take like a 7-minute break? Let's take a 7-minute break. So we'll be back at 11:15, and I'll let time go over a bit into lunchtime. So yeah, so let's see. So I don't want people to kind of feel short, but I just kind of time's up and I'm gonna bolt. But let's take our little break here. It would be nice. Actually, I don't mind getting a cup of coffee. All right, we'll be back at 15 after. All right, everyone. Yeah, we're gonna do them all here, so don't worry. So we're gonna get to the tougher ones. But anyway, I think somebody wanted me just to kind of show. I hope this is kind of clear. Then the next question then is in extended relational algebra, give the sets paired with a number of objects in the set. Okay, I'll just do that one very quickly as well. All right, so basically, we only need to use these ones here. So I'm going to basically say set, and I'm going to do a natural join here within. Okay, so this is going to give us a, well, actually, this is going to, no. Actually, I'm going to do that. In, okay? In is kind of the core one. So we want the number of objects in each set. All right, this is the in right here. There's the objects and there's the set. So basically all I'm going to do is I'm just basically do a gamma over that, where I'm going to get the SID, and I'm going to get the count of OID. And this isn't showing here. Damn it. Oh, here. gamma, the set ID, and then the count of the OIDs, and I'll just call that num, and then we're just going to do that over in. Okay. So that's the most direct answer to the second one about the set IDs paired with number of objects. Okay, here we go. So in tuple calculus, the sets that are a superset of the set with SID 1. All right. What sets are a superset of the set with ID 1? All right. So basically, what this is a not-exist tuple calculus. So basically, it's this. It's that. So think of it this way. I want. Well, I know I want this. I know I want. I'll just say X such that it's a set. This much I know. I want a set. And what property does the set have to be? Well, the property of the set has to be that there does not exist an element, there does not exist an object that is in set number 1, which is not also in the set X, right? So we can do that. Let's do that with a universal, all right? Do we answer these questions in a? No, I'm gonna. That's the whole thing. Is that that's what you guys turned me on to just a second ago. I'm gonna have you guys do some in PDF. So when you have a question like this, you're gonna grind this out and you're gonna write this on paper, and then one way or in what other tool you want or whatever, and you're gonna put that into a PDF. Okay, good. All right. So let's do it using the universal. So remember, it's a very specific question. It's about the set. That is a superset of the set number 1. So that means that basically this means the set X and for all objects. Okay, so I'll say for all O for object. First of all, it's an object. And there exists Y, and Y is an in, right? Y is an in, and Y is Y dot set ID equals 1. I'm sorry. Ugh. And Y dot OID equals O dot ID. All right. So it's saying this, saying for all O's where they're an object, and there exists a record of them being in a set, and that set is 1, that implies that this same object here is going to be a member of X. So that implies that there exists a Z and Z, I'm sorry, Z is a record of being in, and Z dot OID equals O dot OID, and Z dot set ID equals X dot SID. Alles klar? Okay, so look, let's again. We're going for the sets that are a superset of set number 1. Right? So those are set, sure. And there's the following case. That is that for all the objects that are in set number 1, there better exist a record of those objects also being in X. Why not OID? I mean, there might be a shorter way of doing this, but you got to be a little careful because I think, I mean, the issue is that do people understand, do people see why this works? All right, let's look into it. Let's do it again. Okay, right here we have, I'm just going to basically say this. We have an object. Let's see. I'm going to give a little bit of a database state. Gosh, I need to write big enough here. Let's say that in has a record of object object 1 is in set 1. Object 1 is in set 2, and object 2 is in set 2. So this right here is the set. I don't know if you guys can see that, probably not. So 1, like an apple, is in set number 1. In number 2, apple is there, and also an orange is there. Okay? So therefore, 2 is a superset of 1. Does everybody see that? Set 2 is a superset of set 1 because set 2 has 1 and 2 in it, whereas set 1 just has 1 in it. All right. I'm trying to steer clear of the pet rock at this point. The pet rock actually doesn't happen here. If you put in pet, okay, if a pet rock hops in here, and a pet rock has a right to hop in here because it says for all O. But the thing is that right here, notice here that we have the implication here. Okay. So we have object and there exists. So these right, I mean, if you really want to get kind of technical about it, you group them this way. So I have object and there exists all, there exists it being in set 1. All right. And then if that's true, if O is an object and it's in set 1, then this. So that basically that just means that a pet rock hops in here, and a pet rock is not an object. Pet rock may be an object, but pet rock is not in set 1. So therefore, this winds up all being false here, and that's it. And the whole definition of the universal is not this or that. So this being true here is what forces this to be tested. All right. So the pet rock doesn't cause problems here. Oh yeah. Okay. Good. So okay now. So we don't have any pet rock problems. So what we have here is we have. So when we look at this right here, so let's just try to make sure that we understand what's going on here. All right. So when I go to this one right here and I say, okay, look, I want the sets. Okay. Now, set 1 actually is going to wind up being an answer to this problem as well because it is a superset of itself. But let's go to 2. Okay. So 2 basically is this. Okay, 2 is that second set. And it says basically this. It says, okay, you're a set. Okay, now for all objects that are in set one, which is it's just one here. It's just this object one is in set one. Okay, so there's only going to be one thing that actually this winds up being true for. There's only going to be one binding of O here for which this is going to be true, and that's going to be where the object is object number one, right? Then it better be the case that there exists a record of that one being in what X is bound to. X is bound to 2 right now. So there better be a record of 1 being in 2. And there it is right there. 1 is in 2. So this winds up being true as well. So there's only one binding where object equals 1 that forces this to be evaluated, and this evaluates to true when it's set to 1. So therefore, X 2, that set number 2 is going to be reported as a superset. Does that help a bit? All right. Now we get into an even more complicated question, which is basically, in SQL, what are the object IDs that can be obtained through a trade given what is in possession? Okay. So this, basically this says, in SQL, we want to say, okay, I have a whole bunch of things in possession, and those are going to then form sets. And then the question is that what other objects can I obtain through trading those sets? One second. All right, so I have another question here, but what would happen if you replace for all objects as there exists an object? Well, I think what you're getting at here, if people see that this works here, then I suppose people could see that this works too. I just put double negation there. That's the same thing, right? That doesn't change the meaning. But what this would do then is when I push, I would be able to push this thing through here. And basically what it will turn into is that it's a set for which there does not exist an object that is inside of set one, and for which does not exist an object in set one and there does not, it becomes a double negation, and that does not exist that'll be a little bit difficult. Let's see here. I mean, there is an equivalent way of writing this whole expression here that doesn't use for all, it uses the not exists. So what is it? Well, in English, it would be something like, give me the sets where there does not exist an object that's within set one where there does not exist a record of that object being in that set, being in set X. So it's, I mean, it becomes rather convoluted to say it in English, but that is that I could push this through. I don't think we have the time. I could push this through and show how we could derive that by pushing this negation through the quantifiers and expanding it all out. But I think actually the universal here is an easier way of describing it. And then likewise, this fourth thing, which is kind of this winds up being, this is like the hard problem on the exam. This is where it's like, I don't know if anybody got it right. Sorry, I shouldn't laugh, but I mean, it's the thing is that there were only 4 people who took it, but I think that it's how do we want to think about a problem like this? Well, you want to step back a little bit and say, okay, in SQL, what are the object IDs that can be obtained through a trade, given what is in possession? Now, there's a little bit of a wrinkle here. That's why it gives me a little bit of pause. Somebody might say, well, do you mean in a trade or through a series of trades? right? Because then it becomes much more complicated, because I could maybe barter, like I could do a fair trade of like some objects. I have a certain set of objects in possession, and then I do a fair trade to kind of increase the, well, to build up another object or whatever. That then I could, so I do that trade, I get another object, and then I can find another fair trade I can engage in, and I can just kind of do this recursively. Okay, so there's a kind of a notion of recursion in this, but what we want to do instead is, I mean, no one even touched that, but I'm just saying that linguistically there is a notion of, well, obtained through a trade or a series of trades. Let's just stick with the non-recursive case, and it's basically a single trade. All right, let's see here. Could you do the tuple calculus on the final exam also? In tuple calculus, I'm not sure if I understand the question I got there. It was a direct question. All right, so how do we even approach this? This is actually an example here of, for me to this is another example of an every, or I'm sorry, a for all. So this would basically be, I'm not sure if I want to do, it's going to burn up a lot of time for me to kind of do the full problem, but let me just give a sketch about how you would go about doing this. You basically say this, you'd say, I have objects that are in my possession, all right? So basically it would be something like this. It would be, give me the objects in a fair trade. Give me the objects in a two set where there does not exist an object in the from set for which I am not in possession. Or give me the sets that I can, first let's do a simpler problem. Give me the sets that I can trade for. The sets that I can trade for are the two sets. Give me the two sets for which every object in the from set is in my possession. Does that make sense? I'm just trying to give you guys a feeling of how you would go about this, how you would think it through. All right. So give me all the two sets where there does not exist an object in the from set for which I do not have possession, or give me all the two sets where for every object in the from set, I'm in possession of it. Yeah, and then, okay, and so that would give us the two sets. And then what we would have to do is we're not quite there completely, because then we also have to give all the objects that are members of the two sets, right? So we have to go through another operation there to get that. But we look at the simpler problem of getting the two sets, and then we once we kind of have that kind of figured out in our minds, then we can branch out. So let's just do that one first. So basically, that would be like, I'll do it in the non-exist way. So basically, it'd be this. We say here, this is a sub-problem. So this problem is on the way to solving the problem, but we're going to basically say this. We're going to say, I want these would basically be the achievable trades. Okay, I want the trades, the T, which are a fair trade. All right, so T is a fair trade. And these are going to be the ones where, okay, I'll do the non-exist one. Okay, and there does not exist a object does not exist an object where the object, so I got the two sets, the in, Here's the trades. There's not exist an object, and that there exists and I'll call it I, an in, okay, and I dot SID equals T dot toSet, and of course the object dot oid equals the in the I dot OID. Okay, so give me the trades now. We're going to do a little simpler problem. Give me the trades. Oh, you're right. It's not. It's supposed to be in SQL. Oof, sorry. Let's just grind the SQL instead. So, but what I'm getting at here is yeah, we have to do the non-existent SQL. Let me finish up with PostgreSQL, and then we'll in Tupelkagos, and then we'll show how we can do it in SQL. Because I started this already. So, and this is actually not the full problem, but we're going to kind of just at least get to that. So anyways, what do we have here? We have the fair trades where there does not exist an object which is in the toSet of that would be the from set. Okay. There does not exist an object where there's a record of that object being in a set, and that set is the from set. Okay. And there does not exist P for possession, where in possession P and P dot oid equals O dot oid. All right, so this is kind of a bit of a bear here, but what are we saying here? We're saying give us. Now what we're doing is we're gonna here. We'll just pluck out just to kind of make this clear. This is the two sets. Okay, so we're plucking out the two sets, the IDs of the two sets, where it's a fair trade. Okay, so it's going to be a record of a fair trade, and it's the two set for that. And there does not exist an object that is in that from set. Okay, and this right here, the from set. This right here is just to make sure that the join of the in goes through and is talking about the in of the actual object we're looking for. Okay, so that's a little bit of cleanup there. There does not exist an object that's in the from set for which we don't have a record of us being in possession of that object. Okay, so this will give us all the sets that we can trade for directly. Is that clear? Is it clear why this gives us all the sets we can trade for directly? Now, SQL version of this, we can just translate this almost to SQL. It basically just be, here, let's just do it. Actually, I can do it right here, maybe. Select T.toSet from, okay, it's a fair trade. Fair, that doesn't, let me do it bigger here. Okay, you basically select T dot 2 set from fair trade as T, where not exists. All right, now we're gonna have a subquery. The subquery is going to be where there does not exist select, where is this going to be? Object ID, select O dot ID, O dot OID from object as O, all right? Object as O, okay, I'm going to do just, I'm going to do in as I. I'm just going to, instead of having another subquery, I'm just going to have it here in the drawing. The SQL can be a little bit more direct here. In as I, where O dot O dot oid equals in dot oid. Okay, because we're getting the objects, and now we want to have the records of them being in something, and it better be that the set ID, the I dot SID set ID, had better equal this to set up here, or the from set rather, the T dot from set. Okay, so because it's a record, so basically there does not exist a record of that, where if there does not exist a record of the object being in the from set of the transaction, there does not exist one of those where, because this all has to be under the same thing, and okay, now here is where it's important that this closes off that. Okay, so the second not here has to be within this this not exist here. So basically, and not exists, and then we have another SQL we're going to put in here, and that's going to be basically select. Let's see here. Okay, select P from in possession as P, where, okay, and then basically now we're just going back to the object here. So basically where the P dot oid equals the object or that oid. All right, so what this will do is this will give us all the two sets that we can trade for. All right, because remember, to do a trade we have to do. Yeah, again, this was just, this is a problem that I put out there just because I wanted to make. I mean, I don't expect everybody to get all the problems right. I mean, this one actually is a little bit long. I'm going to try to figure out something that's kind of, I'm not sure if I'll do that where I'm going to put the hard stuff, but this is the hard problem of the batch. So yeah, I mean, it's just mostly like if I see the person's kind of going in the right direction, I'll get a lot of partial credit. So there was a lot of, I can't remember how this graded, but I didn't have that many people taking the exam last time. But this is a little bit unwieldy. I regret this would not be a good thing for a first exam. This is too big. But basically what you do is you wind up looking through and seeing kind of if it's following, if it's on the way toward the right problem, the right answer at least. Now the thing is, this is not even there yet, because right now what we need to do here, we could, in SQL, it'd be easy to do. We'll just do this right here, and then I can make this all as I'll call it S for the sets, and this will be all in a from. All right, now there's some other stuff up here, and there's some stuff down here to do the joining. But basically, since I'm getting all the two sets, all I have to do up here now is to kind of thread it through so that I can grab out the actual objects in those two sets. Yeah, it's well, you know, I mean, anyways, that's what it is. All right, so let's see. What do we? We're probably not so well on time here. Yeah. Okay, so people want me to kind of move on maybe to ER. Let's see here. Which ER problem do people want me to do? And I know that someone said, how do we know? One second. Well, the ER diagrams, there's going to be, there are different ways that I can, so somebody asked, how do we know to choose between the normal ER diagram and the ISA ER diagram? So there's kind of different things I can do with ER problems. I can basically say, I can have a description like in English of some kind of, you know, domain. And then I can basically say, go from this to an ER diagram. All right. So I want you to kind of do your best to kind of encompass the requirements in the description. And then I want you to write out an ER diagram. All right. So you could do that. That's one possible question. Another possible, so this is kind of like, I'll call this the how should in possession be in this? I don't know if there's like in possession. Anyways, I'm just going to, these are the type of ER questions I can ask. Because I had somebody was asking like, well, what kind of, how do you know to use an ISA or not an ISA or whatever? If I give you a description of something, like I say something like, well, we want to model, you know, I don't know, vaccine dispensary, a vaccine does this, and, you know, or it gets delivered here, blah, blah. I give you a description of the scenario. And I say, I want you to kind of scratch out an ER diagram. Then it kind of, it's kind of a judgment of whether or not you, I can look at it and see, did you do kind of a nice job? Or was it just kind of cat scratch and doesn't make any sense at all? So it's kind of like, in that case, it'd be like, or did you just kind of not really want to even deal with it and you skipped it? So if you did, or you just kind of write down like, just like some really small, short little, it's just like, it's not even, it's like, I have this kind of full paragraph and all you do is have like 2 boxes or something. It's like, okay, or you don't answer at all. That's when you get 0. Then I look and I see somebody, you scratch it out, but like the syntax is kind of messed up on the diagram, and or you're just missing like some fundamental many-to-many relationship or something or other. And I'll be like, or you did a really good, it looked like you really kind of went through and you have a, you know, fairly good design. So basically it's going to be 0 points to 50% to 100% of the points. All right, that's one type of ER question. Another type of ER question is I give you, and you know, and I just for my own sake in grading, I'm not going to have it. So okay, now take this and then convert this to tables. No, because there's too much divergence. But another type kind of problem is I have basically here is an ER diagram. And I might, and if it has an ISA in it, then you got to deal with that. And you know, something like this. But it's very tight, and it has like attributes and they're underlining this. And I say, I want you to go to a set of tables. And I basically say, when you go to set tables, I want to see the foreign keys marked, and I want to see the primary keys marked. All right. That's another kind of ER type of problem. And with that, if it's empty or if it's just like complete cat scratch and it's like it doesn't even look like an ER diagram. It's like just like a bunch of blobs and stuff like that with names on them and just, well, no, I'm sorry. If we get to right here, if it just looks like there's a complete like breakdown in terms of like the rules that were used to kind of map this over, then you're going to get very little points. But if it looks really clean and it looks like you systematically went through the spell out algorithm, or the algorithm that takes the ER diagram, then you're going to get, most of the points for that. But you need to have the foreign keys and the primary keys marked. Okay. But I'll say this when I put them in. And then let's see, is there another type of ER diagram? What other kind of ER diagram questions? There's the description to the ER diagram. There's a nice stable ER diagram knocked out to table, and then you have to put in the tables here. So this is like this is the question, and this is what your answer has to be. Is there any other type of ER diagram question that would come up? Let's see. 19.2. All right, so I got to go back to my exams here. All right, so there's an ER diagram here. Yeah, so this ER diagram on part 2, it's big, so I can't do it all right now, of course. But that's a class of this type of problem where there's like a big ER diagram, and you got to push a button on it and knock out the tables. Relational scheme to ER, that's an interesting question, but we never really covered that. Yeah, I mean, we never covered, we never went. And I mean, some people can do that. I mean, I don't know. It's an interesting question. Like, how do you go from relational schemas to ER? And then if you do that, what is really the point of it all? But what is the difference between total and partial participation in tables from an ER diagram? Well, there's the kind of the semantics of what does a many-to-one relationship with the rounded arrow, which means that every one of these has to have every one of these has to point to one of these. So this one where we have this. Not every one of them, but at least some of them. Well, not everyone has to have one of these. Okay, so it could just basically be empty. They don't have to participate in that. So what that means actually in the case here, it means that the value for the foreign key, because the foreign key of the key of this guy right. Oops, sorry, you guys can't see that. The key of this guy right here is going to wind up going over to here when the tables get defined. And in this case, it just allows that to be a null value. Yeah, no arrows means many to many. Yeah, so this is what part 1 are you referring to in part VT22? What part 1? Yeah, okay, actually, so in this case here, it looks like on that exam last year, I did a little bit of a funny variation where I did say basically, can you build an ER model from the database? So how would we do that? I mean, then it kind of just becomes more of a common sense thing. I mean, it's pretty clear that what we have an object. So now you got to, the thing is that not everything is like, you got to be a little bit flexible not flexible, nimble. So nimble in the sense it's like, well, he wants to say, we're going to go back and we're going to look at the schema we had. And now let me see if I can grab the schema. Here. So he wants me to go from this thing here and backward engineer an ER diagram. Yeah, how would we do that? Well, there's one thing that's for sure. One thing definitely for sure here. If I ask you, what would be a good kind of control or a good way to do a little bit of quality control over what the product is here? Well, one way to do that, let's just be nimble here and think a little bit. One thing is that whatever ER diagram we reverse engineer from this, if we push a button on that ER diagram, this is going to plop back out again, right? That's one way you could say that, well, how would you validate that it's a proper ER diagram? You would say that, well, if I generate it and then I push a button on it, I should get back my same tables, right? So maybe that would be kind of a way. So actually, that's kind of interesting. So this kind of means that there is another kind of, there is the notion of a problem of basically saying reverse engineer it. But when you reverse engineer it, make sure that whatever you reverse engineer, if you push a button on it, you get back what you have. But let's just use a little bit of common sense here about about this schema here. So it's pretty clear we're going to have, okay, it's pretty clear that a set, let's see here, is going to be an entity. And it's pretty clear here that an object it's pretty clear that an object that, in a particular defined set, an apple can be in many different sets, and a set can have many different objects. So it's definitely many to many, right? And then we have the notion of a fair trade, and that's got a from set and a to set, all right? So we have some different options of that, but what we could say basically here is we, I'll do it this way. Make this a relationship. From to. Okay. These are roles, by the way. We talked about it just briefly, but these are roles. So from and to. So this is the way we're doing it as a verb. We can nominalize it and we can make it and have then one-to-one relationships, but that's just, this I think works pretty well, actually. So then we have a from and to, right? Sets goes, and there's many sets can be part of can be part of the from, and many sets can be part of the to in the fair trade. Fine. And then we have in possession. Now, in possession is a little bit, I think somebody was kind of bringing this up. So in possession, I mean, there's this kind of notion of it. Okay, so an object, how do we get in possession to work? It's like this. I mean, you can see it like this, is that let's say home. Not right. That's a little bit tricky. So we got to think about this for a second. So there's one way of doing it is basically just having a Boolean called in possession. But that won't let us reverse engineer the original tables we have. We have this in possession winds up just being a unary. So how do we get this out of what we have an object? Well, there's one way we can do it. Objects, by the way, have OIDs. Is a. in possession, I'll put object just to get the name. And there's a, so you have an object, and then there's a specific subtype of object, which is one that's called in possession, right? And I think we got it now. Now, so if we do the ER model of the ER model of ISA, the ER, I'm sorry, the ER ISA resolution, then if you push a button on this thing, boink, then the original, this table is going to plop out with proper foreign keys. Okay.
Michael, I have a question.
Sure.
Is it possible that in possession could be a weakened entity because it depends on object, and the relation between them could be contains or in?
So you're saying instead of doing it as an ISA here, we could do it as a weak entity.
Because to have something in possession means that you need to have an object. So it depends on it. And you could have many objects in possession.
Yeah, that's good. That's but let's see, is that in possession? I mean, generally speaking, just my own taste. But I mean, some people do. Some people have different tastes. I think that what you're saying is reasonable. Just in my own practice, I generally disdain weak entity types. I don't like them. I mean, they don't make much sense to me. I mean, like, I don't have a good intuition around them. Sometimes I do. Sometimes it's kind of obvious, like with a dog or something, where the dog's identification depends on the person. I think that certainly, if you had done that on the exam, I would be perfectly fine with it because it's legitimate. But just in general, I mean, generally speaking, if I had my way, I think we would just get rid of weak entities. But I can't do that. There's reasons to have them, so I can't. But I don't use them. I try to avoid them myself.
Okay. Another question: is it a typo in part 5?
Quite possibly. Let's see. Part 5 of that. I mean, I probably have a typo in there. Where is it? What is part 5? What's it about?
Encode a standalone XML document, and then you refer to part 1.
No, I should refer to part encode. Oh, one sec. Upload an ER model. Wait, I mean, encode. Upload an ER. I mean, it should refer to part 2. Oh, in part 1. Part 2, rather. What was part 1? Part 1 is just yeah. I think people just kind of sent me again. Remember, I kind of was I only had just a handful of students taking this exam here, so yeah, it should be part 2. Absolutely.
Okay.
Yeah, well, so you're right. It was a typo. And then, of course, that is like just a really, I mean, it's a nasty question because it's going to be terrible on your hand because you're going to have to, I mean, this is kind of doing XML. But I don't know, it's not that big. But the thing is that the fact that I have like 6 objects, it's just like it could get that was actually one of those things where maybe because of Cambro, it's easier to do that because you can just kind of like code it up. But but if you have to do that with on hand, I mean, how many participants? We have 67 still. Is there another? I mean, I can keep on going here. I mean, I think the thing is that I mean, it's like with anything. I mean, I don't know. I mean, you might sit there and kind of be bitter about it by saying, like, God, I mean, all this work to kind of try to get these things. But the thing is that I don't know. My experience was always that, like, I learned a lot on just writing the exam, because under the exam is like one final opportunity to get work out of you guys. And then when you do work and you kind of have to try to figure things out, you learn stuff. So there's nothing wrong with learning something new as you're doing the exam. You know. No, 5 and F and 6 and F are talked about in the textbook, but you can skip those, like projection key normal form and stuff like that. That's I'm not going to ask any questions on 5 and F or 6 and F. If you're interested, you could read about it though. Yeah, we didn't cover the 3-tier architecture, but I should at least mention what it is, kind of. So the 3-tier architecture is this idea that you have a bunch of stuff running. 3-tier architecture is like this. It's like you have the browser. And how do I write the browser? And then you have the browser talks over, usually is like HTTP. And then what do you have here? How do I want to write this? I'll write this like that, although that's not quite right. And I'll call this the, let's give it a name, Flask Python. It's some kind of middleware. And this guy talks out to the DB. This is the 3-tier architecture. So the first tier is like kind of the UI, front end browser. The middleware is kind of where your business logic is, and you know, like the things that are preparing the like the actions and the model, or the model, the view, and then the presentation, the style, or whatever, up there. But and this usually, at least depends on what this is. Kind of, this is my favorite stack, where you have so this is what's running inside the browser, everybody. We never looked at this stuff. JavaScript. And not just JavaScript, but React JS. All right, so this is good stuff. And then you have like Bootstrap, maybe you bring in here. Bootstrap. You know, that's CSS framework. So yeah, you're running up here, and then you got your business logic in the middleware, and this is you do this in Python. And then on the back end, then you have your model inside the database. That's like, this is a very common architecture. Although people are saying it's changing now, because you have like this GraphQL and stuff like that. This doing some more stuff in the browser. But anyways, we're not going to cover that. But that's just what I would say. All right. Are there any more questions? Let's see how many participants do we have here? Oh, we're holding up on the participants. Unfortunately, I don't have the full solution sheets for the older exams. I'm sorry. Yes, it is an open book exam. Somebody pointed out that the Cambro site, I updated the Cambro site to make that clear. Yeah, I mean, you're going to be given a lot of time to do the exam. So, in fact, you're going to be given a lot of time. Yeah, the exam is going to be given under the test quizzes on Cambro. And you're going to have a lot of time to do it. So, So just take your time and do the work. I mean, a lot of it is like showing up, right? I mean, there's that old quote saying that 90% of life is showing up, and it's true. I mean, you know, the worst thing you can do is just kind of have like really small, like short little answers and kind of skip a bunch of stuff. I mean, if it doesn't feel like, if I don't feel like you did a lot of work on the exam, you know, it's got to, you know, there's got to be like, I mean, you know, it just, I mean, I don't want to start, I mean, work, you know, I don't know, what can you say about work? I mean, it's what counts, I guess. I mean, you don't want to do too much of it though, but it's what makes the difference. I mean, the way it's going to run on Cambro is that it's going to be countdown quiz. I'm not really sure what that means. No, it's going to run as a quiz on Cambro. So you're going to upload. So, for instance, when I do when the ER problem comes up, I'd say, well, you know, put stuff on PDF, and then you construct that yourself, and then you upload it on that particular problem. And then there'll be other problems where you have to type in the answer. So it's not going to be like you upload a giant PDF of everything. It's going to be, yeah. Again, remember, generally speaking, there's going to be, maybe I can even try to like put like a little star behind. There are going to be certain problems where it's going to be like, I'm going to make them difficult. And then there's going to be some problems that's going to be kind of standard, just showing the work. And most of them are going to be standard, just showing the work, so that people who do an honest job of studying are going to be able to pass. But if you want to get a 5, I mean, then it's like, you probably have to do well on some of the hard problems. I think I'm going to actually mark how many points things are worth. Yeah, you guys, I mean, if you want to do something on the side where you're going to, I don't know what you mean by, okay, you can use paint or draw. That's fine. And if we have to do an XML, oh yeah, that's right. Do it. Yeah, exactly. So if you have to do some XML work, definitely try to do it in something like VS Code or whatever, or I don't know. I mean, I use Charm, PyCharm. I'm kind of I think it's because I'm just so invested in PyCharm that I've kind of avoided VS Code, but VS Code is free. So is PyCharm community, but yeah. Okay. Yeah, the grading policy is on the web. So if you want to see the number of, what the breakdown is, it's like 200 points for the recitation total, and then 800 points for the exam. So what that means, it means if you skip recitation, you're never going to be able to get a 5. If you guys want to look at that stuff, it's on the Canberra thing. I think you have to have 500 points to pass, and then it's 650 to get to a 4, and I believe 800 to get to a 5. But don't quote me on that. It's all, I mean, I think that is right. But yeah. And people who don't pass are the ones who don't do. I mean, that's almost always the case. That people will hand in something that's kind of half done, and yeah. Anyways, I mean, if you guys are interested in database stuff, I mean, definitely consider taking 5DV187. Remember, databases are great because, it's like a trade. Trade meaning that it's something that if you know databases and you can work them, you can get people to pay you money to do. It doesn't matter. I mean, there's no politics. There's no like, it's not who you know and all that stuff. It's not. It's what you know. When it comes to database, it's everybody says, oh, it's not who you know. It's not what you know. It's who you know. But when it comes to databases, it's what you know. And then can you halfway work together with people? But yeah, there's a big demand for it. A big demand, and so it's you're not gonna. I mean, if you know databases, you're never gonna be on the breadline, right? Well, unless you never know. I mean, things can happen, but I'm just saying that you're not gonna be. Yeah. What can I? How can I put it? You can definitely do something of very concrete value in the world. It's not something where it's a dubious value. It is valuable. So people are willing to pay money for it directly for the skill. So I highly recommend 5DV187. So that course begins September. God, I really hope we can run that course without COVID restrictions. This sucks. I'm so sorry. Well, I kind of joke about it sometimes and say it's kind of nice in a way, but it isn't. Actually, it sucks. I mean, there's no sugarcoating it. It sucks. COVID sucks. And having to yeah. Anyways, what can we do? Yeah, I mean, I remember there was some guy who just like said he was so sick of it. He just headed down to Stockholm town and said, "I'm going to get the thing, but I'm not going to do that. I don't want it. I really don't want it." But people like this bug chasing, they go after it because they just don't. They're so sick of being paranoid about it. But the problem with COVID is I think you might be able to get it twice. So hold out for the vaccine. But but anyways, yeah, the database course is going to be in September. And by the way, in that database course, if you have like there's a big project in that course. So if you have an idea of some giant, you have an idea of like some company you want to start or something like that, something entrepreneurial, then that class is where you can propose that you can get like a group to work on a project. Yeah, I'm holding the advanced version. There is nobody else. I mean, I'm sure there are people. Yeah, I mean, there are people who could teach it, I guess. But it's my course. I mean, I do the beginning database course and the advanced database course for now. So it will be me. Yeah, it's next fall. It's going to be this September. No, it definitely. I mean, I could make it more theoretical, but definitely it's not like going into more like unless people want me to. If people want me to do more like advanced like logics and stuff like that, but the person who's direct messaged me just said no. So you guys don't. I mean, I can understand. Yeah, you don't. You want to. It's going to be a lot more on transactions and a lot more of the advanced features of SQL, and it's just like this. I can kind of like make little side comments about the more mathematical stuff, but we're not going to do that. And I might actually try to do some stuff with Cockroach because Cockroach is kind of. I mean, I haven't checked back in like the last month or two, but I think Cockroach is going to be a big deal. So for like transactions and kind of more like horizontal scaling or car ID. No, that is not well formed, by the way. It has to be equal. Car ID equal to. That would be well formed. This was just a comment on the chat, by the way. So anyways, I mean, if there aren't any more questions,
That would be well formed if there's no internal tags. That's right. But you have to have the equals, the ID equals to. That was all. That was my comment, which is on the attribute was where the problem was. But sure, you can close off tags that way without that tags that have no bodies get closed off that way. I thank you very much. There was a compliment. I don't know if I deserve it though. But I'll take it anyways. I mean, I don't know. I just, for some silly reason, like this stuff. I don't know. I mean, a lot of people don't like databases that much. I like them. I mean, I just think it's kind of, yeah, it seems like a nice little controlled world. Yeah, I think so. Again, I always say that I think that The Matrix, like that movie, The Matrix, it is definitely running on a giant database. I mean, how else would you control all that stuff? I mean, how else would you you have to have a conceptual model of the Matrix world. You can't just do it with like all these giant programs running around. That'd be nuts. Who's ever going to put that together? The only way you can put the Matrix together is if you have a nice, very, very clean, well-designed conceptual model, like an ER diagram, an EER diagram that kind of governs everything. And then you have a lot of triggers. Sure, you have a lot of programs running around, but you have you must absolutely have some kind of overarching conceptual model. Otherwise, you'll never be able to design that thing. I mean, somebody could say, oh, well, there's going to be an AI that's going to come up with a conceptual model. Well, that's fine, but there's got to be a conceptual model. I mean, it's not going to be just like a giant neural net, right? Yeah, that would be a good idea for, I don't know, the problem with that extra, it would be fun, but the question is that, you know, I mean, this is one of the sad things about like, well, I should really watch it here because I'm being recorded. But I mean, the thing is that the way X jobs work is you have to have a way you evaluate things, you know. It's too bad. I mean, what fun projects are is that you just kind of do something and you just see how far you can take it. And you get more experience and you can kind of, maybe you can even create something that's kind of really cool. I mean, you know, and, you know, does something or other. But the problem with like putting stuff in terms of X, it's not a problem. I mean, I understand why it has to be this way, but the kind of scientific method is that you were supposed to kind of create new knowledge, not new programs. So it's a big trick of how to kind of get creative work, like doing something like trying to create the matrix and shoehorning that into kind of the definition of what a thesis makes, or what a thesis, how a thesis is defined or should be defined, or the kind of the standard way that they get evaluated. There's been many theses in computer science that have started out with just a lot of fun doing something like trying to create the matrix and ended in a lot of tears because of the way someone just says you don't have a problem statement. I mean, what was your problem? Your problem was you wanted to, well, I guess you say my problem was to create the matrix, but they'd say that's too broad. You need to have something much more specific that can be tested and accomplished. So I'm not really sure if it's a great idea, but it would be fun. Sometimes the fun ideas aren't so great, or not so, I don't know how to put it. No, it would be problematic. I mean, it would end badly if you try to create them. If you said my thesis, I'm going to try to create them. If you say I'm going to try to create like some aspect of it, like say I want to do the temporal spatial modeling for, it'd be really tough to kind of get it. So, I mean, you could do something where you say, well, what about, I don't know, come up with the two different approaches to create the matrix. You say, here's a thesis idea. We're going to kind of evaluate what would be the pros and cons of doing a very simple implementation of the matrix. One using like SQL alchemy, using kind of a one of these object relational mappers, so that you're doing everything inside of Python, and then you're just using the database as a persistent store, versus you're doing it all as like say stored procedures and triggers. So what would be like, okay, it's still not specific enough, but you have to come up with like a very simplified matrix world that you want to simulate. And then you would say, well, let's try to do it with ORM, with object relation mappers and like SQL alchemy. And then let's try to do it with just kind of standard relational databases with an ER diagram and triggers. Maybe. The problem is you probably get bogged down like creating the matrix in the first place. But maybe if you could get it down to like 10 or 15 tables, essentially, or just kind of a really super simplified matrix, then maybe. Then you could like test scalability. You could maybe have something to say in terms of something concrete to say, but it's still pretty broad. Somebody asked, yeah, I always feel like I have to have some XML question on the exam. Yeah. I mean, essentially every lecture has to find a place on the exam. Every lecture has to have a happy home on the exam. Otherwise, I mean, yeah, there'll be XML. Well, participants are still probably like hanging around, probably get well, you got some advantage, I guess, for hanging around. So 90% of life is like showing up and hanging around. All right. Okay, guys, if there's not another question, I think we'll just call it a day here. Okay, yeah, well, then good luck on the exam. And I look forward to all of you, every single one of you being in database 2. Actually, that would be bad because it's got a limited enrollment. So I think that it's probably not going to happen anyways. But yeah, still, the more the merrier. Okay, catch y'all later. Go to time edit if you. I just see go to time edit if you want to know when the exam starts. But it'll be pretty clear when I do the release. I mean, yeah, it's on Thursday. All right, I think it was Thursday, right? I mean, well, I should. Sorry, I'm just being stupid here. When was it? I'm almost certain it's Thursday. If it's not Thursday, if it's Wednesday, I'm not going to be very happy. Time edit. So if I go here, time edit schedule, click, and then time edit always starts at the beginning of the term, which is kind of bugs. So I got to now go scroll through all the weeks, and that's right. It looks like the exam starts at they have this as a for 13:15 according to this to 1700. Yeah, okay. All right, catch y'all later.